This video will be really quick. It's just one additional example that was left over from our set of slides in our last class on electric potential. So this will just be, think of this as a review of what we had been talking about before spring break. So we have a very large plate, and of course as soon as you see very large you want to think infinite plate. When we have formulas, we have a formula that deals with that situation for an infinite plane of charge. And so a very large plate has a charge density of 0.100 microcoulombs per square meter, positive. Okay, so question A is, how far apart would the equipotential surfaces of 150 volts and 200 volts be? So let's draw a picture. Here is our very large plate, and we're looking at it along the side so that we can draw, to the left and to the right of it. So this is just edge on, right? And we have electric field lines coming off of it. And just as a reminder, the electric field due to an infinite plane of charge is uniform. Really important fact about this situation. So they're uniform, and they're just going in, since it's positive, they're going straight out away from the plane on both sides. Now the potential then will consist of perpendicular lines, right? The potential field, equipotential lines, are always perpendicular to the electric field lines. So they would just be going like this. So each of these lines represents a certain potential, a certain number of volts, and on this side as well. And we're free to make V equals 0 anywhere we want. It doesn't really matter. It's mainly the changes in voltage that matter. So I'll just pick two of these to be the 150 volt and the 200 volt lines. So let's say this one is 200 volts and this one is 150 volts. And the only thing I do know is the potential should go down as we follow the arrows on the field lines. So if you follow the field lines, you should be going downhill. You should be your V should be going down. So since the arrows are in this section are going from left to right, my 200 volt line should be to the left of my 150 volt line. Okay. Okay, now let's do the math that answers the question. So the operating formula in a uniform electric field that connects that electric field to the potential is delta V equals E times D. Right? The change in potential is the electric field times the distance. So we are looking for the distance, right? That's the question, how far apart. So D should be delta V over E. Okay, but we know E from our charge density. Charge density is sigma, and we remember from our electric field handout that the electric field due to an infinite plane is sigma over the constant 2 times epsilon naught. So I'm going to sub that in right here. I mean, I could figure that out separately and get a number, or I'll just plug in that expression right now. Since E is in the denominator, it's going to be the 2 epsilon naught will be up here with the delta V, and the sigma is down there. Okay, so now I'm going to plug in the numbers. I have everything. There we go. And 50 volts goes in for the potential change because we're going from 200 to 150. And that works out to 0.00885 meters, or 8.85 millimeters. Okay, so that's part A. Now question B. If an object of charge negative 2.00 times 10 to the negative 6th coulombs moved from the 200 volt to the 150 volt locations, would it be going faster or slower, and by how much? All right, let's answer the faster or slower part just qualitatively. Of course, when we get to the formulas, if we put in our correct negative signs the right way, then that'll tell us as well. But let's just think this through first before we get to the numbers. Remember that we think of potential as altitude. And so going from 200 to 150 is like going downhill. And so positive charges, right, if you roll downhill, you would tend to pick up speed. And that's what positive charges do. Positive charges act like that. Positive charges would get faster. However, we have an object of negative charge, so everything's the opposite. So because it's negative charge, going downhill, quote unquote, really means you're slowing down. Okay, so the answer is slower. But let's see if we can figure out by how much. Let's get this. Let's figure out the velocity change. And by the way, I'm assuming that no other force is acting on this object. Obviously, if another force were involved, that would change things. But let's assume that it's just kind of moving on its own, or I should say only due to the electric field that's present. That's the only thing that's making it go slower. Okay. All right. So for this, we're going to use the energy approach, and change in potential energy is Q times change in potential. All right, so we have the charge, and we have the change in potential, and the charge goes in as a negative, and because we're going down, we're going from 200 to 150, our delta V I can put in as a negative 50 volts. I didn't worry about that back here because we were just doing magnitudes up here. But here, and I don't have to do it here because I already did figure out that it's slower. But I'm just going to show you that if I actually am careful about my pluses and minuses, things work out and will give me this answer as well. I don't have to, but because we already answered that, but I'll do it anyway, just as a backup, a little check on this answer. Okay, so when I work this out, I get a positive, right? I get 0 point, and it turns out to be 0.0001. 00. All right, and that would be joules. 0.1 millijoules, if you like. And that's positive. So the potential energy goes up. Okay, so now I say, well, since potential energy goes up, and because there are no other external forces, this is an isolated system, therefore, I know that my overall energy, my mechanical energy, can't change. So the change in kinetic plus the change in potential has to be 0. So if potential went up by this number of joules, kinetic must go down. By 0.1 millijoules. And there you go. So the kinetic energy goes down. That, of course, means that it goes slower. All right. So now, actually, we can't really answer how many meters per second it goes down because I didn't give you the object's mass, and we don't know what the initial velocity is, right? So, I mean, at this point, if we had the information, we could solve for, say, final velocity. If we knew the mass and the initial velocity, we could solve for final velocity. That wasn't included in this problem, so we can't actually convert to meters per second. But we can know how many joules of energy were lost from its kinetic energy, and in that sense, we know how much slower it's going. Okay.